Hello and welcome to a short lesson on exponentials and logarithms. In this lesson, I'll point out the fundamental relationship between exponentials and logarithms. I'll state the three laws of logarithms, and then we'll put them to good use solving three A-level problems. First of all, these two statements are equivalent. Log y to the base a is x and y equals a to the x. And we can't tackle logarithms until we're comfortable moving between those two statements. So the log of y to the base a tells you what power a must be raised to give you y. Now let's look at two or three examples. Log 100 to the base 10 is 2 is equivalent to saying 100 is 10 squared. So what we're saying here is that the log 100 equals 2 means that 10 must be raised to the power 2 to give you 100. Look at the second one. Log 16 to the base 2. 16 is 2 to the power 4. So the power to which 2 must be raised to give you 16 is 4. And that's why log 16 to the base 2 is 4. Log 27 to the base 3 is 3, because 27 is 3 cubed. But of course, most numbers, if you take the logs, you don't get a perfect whole number because they're not perfect squares or perfect cubes and so on. And one special base is e. It's a number which crops up naturally, rather like pi does. It's approximately 2.718. Can't be written exactly. And instead of writing logs to the base e, we write ln, the natural log, and that's what it will say on your calculator for that base, ln. So the natural log of 60 is 4.09, which means 60 is e to the 4.09. Now let's look at the laws of logarithms. These are easily proved from the laws of indices, but I won't do so here. All these logs are taken to some base I'm calling c. And if we have the log of a times b, it's equivalent to the log of a plus the log of b. If we want the log of a divided by b, it's the log of a minus the log of b. And finally, if we want the log of a to the power b, that's the same as b times the log of a. Now, we need to be able to go both ways with these results. Sometimes we'll want to start with the right-hand side and move to the left. Sometimes we'll want to move from the left-hand side to the right. Now let's have a look at some important results that fall out of this. First of all, the log of a to the base a is 1 because a to the power 1 is a. Even more important perhaps, the log of 1 to any base is 0 because a to the power 0 gives you 1 regardless of what positive number a happens to be. And finally, if you've got the log of 1 over b, you could write that as the log of b to the power minus 1. But we can pull the minus 1 outside the log and it's the same as minus 1 times log b. So the log of 1 over b is minus log b. Before going on to solve some problems, it would be useful to have a look at a typical exponential graph and a typical logarithm graph. So let's have a look at y equals 2 to the power x. So there's the graph of y equals 2 to the power x. And all exponential graphs like this go through the point 0, 1, because when x is 0, 2 to the power 0 is 1. And if I was using a different base, such as y equals 3 to the x or 4 to the x, it would still go through that point 0, 1. It may look as if the graph is on the x-axis, but in actual fact it's slightly above. It doesn't touch the x-axis. And now we'll have a look at the graph of y equals log x to the base 2. And this one is in fact a mirror image of the graph of y equals 2 to the x in the line y equals x. Let me put on the line y equals x and you'll see. One is a mirror image of the other. It's the inverse function of the other. Now what can we notice about this log graph? Well, first of all, notice that when x is 1, the log of 1 is 0. And that doesn't matter what the base is, log 1 is always 0. It may look as if the graph is on the y-axis, but it isn't. If I zoom in, you'll see there's always a gap. In fact, log x is not defined for x is 0, it's only defined for positive values. And as x tends to infinity, log x also tends to infinity. But it does so very slowly because it's got a very shallow gradient, and it's, in actual fact it's 1 over x. So as x gets very big, it gets flatter and flatter, but it's still tending towards infinity eventually. Now let's solve some A-level problems. Solve 2 log x plus 15 minus log x equals 6, both logarithms to the base 2. And in these kind of problems, the logarithms will always be to the same base. Now we can't collect logarithms together when we've got different amounts of the two logarithms. So what I want to do first is take the 2 inside the log. So using the third law, 2 log x plus 15 is the same as the log of x plus 15 squared. So that minus log x is equal to 6. Now I can say log of a minus the log of b is the log of a over b. So I can write this as a single log on the left hand side, log to the base 2 of x plus 15 squared divided by x is equal to 6. And that means that x plus 15 squared divided by x is equal to 2 to the power 6, because the logarithm of that expresses it as a power of 2. So I can now say that x plus 15 squared is equal to 2 to the 6, which is 64, multiplied by the x. Expand the bracket and we get x squared plus twice the product is 30x, plus 15 squared is 225, equals 64x. Now bringing the x's to the left hand side, I've got x squared plus 30x minus 64x is minus 34x, plus 225 equals 0. And this factorizes. Two numbers which multiply to plus 225 and add together to minus 34 would be minus 9 and minus 25. So the implication of that is either the first bracket 0, and if x minus 9 is 0, x equals 9, or the second bracket could be 0, in which case x minus 25 is 0, x equals 25. Example 2 is in two parts. First solve log y at the base 2 equals minus 3. Well, here we simply write y is 2 to the power minus 3, because that's what the log of y means. So y is equal to 1 over 2 cubed. So y equals 1 over 8. And we'll use that in the second part of the question. Solve log 32 plus log 16 divided by log x is equal to log x, all logs to the base 2. First we'll multiply through by log x to get rid of the denominator. So we end up with log 32 plus log 16 equals log x squared. But 32 is 2 to the power 5, so log 32 to the base 2 is simply 5. 16 is 2 to the power 4, so log 16 to the base 2 is 4. So 9 is equal to the log of x squared. So I just need to take the square root of both sides. The square root of the right hand side is log x. The square root of the left hand side is plus or minus 3. So either log x is equal to 3, which means x is equal to 2 to the power 3, since the logs are to the base 2, which gives x equals 8, or log x equals minus 3. And we saw from part 1 that that would mean that x is equal to 1 over 8. Our final example, example 3, is also in two parts. First, sketch the graph of y equals 7 to the power x. It starts just above the x-axis and it goes through the point 0, 1. That must be marked on the y-axis. Next, solve 7 to the power 2x minus 4 times 7 to the power x plus 3 equals 0. Here we need to realise that this is a quadratic equation in 7 to the power x. So 7 to the power x is the variable instead of the normal x. Here we have the 7 to the power x term and the square of it 7 to the power 2x. We can factorise this. 7 to the power x in the first bracket, 7 to the power x in the second bracket, and we want two numbers that multiply to plus 3 and add to minus 4. So they would be minus 1 and minus 3. So either the first bracket is 0, in which case 7 to the power x is equal to 1, and that implies that x equals 0 because 7 to the 0 is 1. Or 7 to the power x minus 3 equals 0, so 7 to the power x is equal to 3. Now to solve an exponential equation like this, we take logs of both sides. It doesn't matter what base we use as long as we use the same base for both sides. So I'll take the natural log. The natural log of 7 to the power x is equal to the natural log of 3. And now using the third law of logarithms, log 7 to the x is x log 7. Now to get x on its own, I simply divide by how many x's I have, log 7 of them. So x is log 3 divided by log 7. And if we put that in the calculator and give our answer to 2 decimal places, it comes to x equals 0.56. And that concludes the lesson.